Hello everyone, my name is Bryan Morris from Ciena, and today I'm going to give you a summary of a paper that my colleague Andrei Tarnauceanu and I have created about how we controlled our hierarchical constraints through layers. So the agenda for today will be going into a little bit of background about what the problems we were trying to solve and why you would want to layer constraints in the first place, as well as looking at some existing solutions that have already been presented through using object-oriented techniques to do the same kind of effect of being able to control and layer your constraints. And then we'll go a little bit more details about what this solution is and what's its value add and what it's bringing to the table. So as I said, we'll go into a little bit more details about what layered constraints means and how we create them. And at the end, we'll finish up with a bit of future work and a bit of a summary about what we discussed. So this is trying to get into the idea of why we would want to layer our constraints. So the constraint language that System Verilog has defined is declarative in nature and is a very rich and very powerful language. And it can be confusing. And as your constraints get larger, and as you create these hierarchy of constraints, it's becoming harder and harder for both the engineer to understand what's going on across all of these constraints, as well as the constraint solvers are great in terms of their capacity, but they do have some performance limitations or some constraints themselves when your constraints get very, very large. So the advantage of separating your constraints into layers is it attacks both of these problems at the same time. One, by having smaller sort of separation of your layers, you'll allow the engineer to understand, they just need to understand what's inside that layer, not necessarily the entire constraint space that you're looking at. And so this helps the engineer in just understanding how to add new constraints, how to maintain the existing ones, as well as when you're presenting a smaller set of constraints to the solver, you'll get better performance aspects. Now we'll go into a little bit of details about what the existing solutions are. So there's one paper and one blog post. There's a paper 2015 from John Dickel about using policy classes to control how constraints are pulled in. I'm not going to go into the details of what a policy class is, just suffice it to say that it's a very good paper. I highly recommend reading it. But the intent behind it is constraints by their nature are more declarative and they're more static. So when you create a constraint, it's usually applied to an object or as an inline constraint, but it's whatever has been compiled. What policy classes allow you to do is dynamically select which constraints are going to be applied and presented to the solver at any time. So you could choose, depending which mode you're in, you could select this set of constraints, set constraint A, and if you're in a different mode, you could select a whole different set of constraints. And at runtime, you can basically present to the constraint solver, your selection of what it means or which constraints you need to apply. Similarly, Tutor Timmy has a blog post on mixins, a couple of blog posts, in fact. And I'm not going to go into what mixins are either, but the intent is the same. You allow you to selectively pick which set of constraints you want to present to the solver. And there's probably other object-oriented solutions that I'm not aware of, but an overarching, theme here and what we've said in the paper is these object-oriented solutions are definitely the way to go if you can, right? So if you're starting from a greenfield approach where you're just creating your constraints for the first time and your constraints are going to get large and they're going to get complex, being able to dynamically select which constraints you want to use through these object-oriented techniques is definitely the best way to go. But what if the schedule doesn't allow you to, you already have a pre-existing large set of constraints, and your schedule just doesn't allow you to refactor those into these nicer object-oriented solutions. So what we do is we want to be able to map our existing random variables constraints into a specific layer. And as I said, in the next couple of slides, I'll describe what a layer is and how we do this mapping. And this technique of being able to look at a subset of your constraints and and variables and apply them to a particular layer is complementary to the solutions above. And we're going to explore that a little bit later as well. And this is there's a lot of boilerplate code that we are going to present a little bit later about how we control and create these layers and attach the variables and constraints to each of these layers. And so what we've done is we created a macro to abstract out all this boilerplate code and allow you to easily define and attach layers and constraints to a particular layer. And as well, the macros allow you to add in more debug information you can use to isolate whenever you have any constraint to solve layers. So let's take a concrete example, or a somewhat concrete example, a simplified concrete example. Let's assume we're going to split the constraints into 3 layers and the associated variables. So in the first layer, we'll call it device mode. And device mode is, sort of the common, top level characteristics of your device that you want to set up. And let's assume then you have a number of slices in that device that then are also dependent on which device mode you've selected. So we have a slice mode set of constraints and variables that are dependent on the variables and constraints as defined in the device mode. And similarly, going forward, you have a block mode, which is also dependent on slice mode. So we split. Now we can attach, if you will, each of these constraints and variables into individual layers. So the device mode will attach to layer 1, slice mode to layer 2, and block mode to layer 3. And as you can see, each layer builds on the values from the previous layer. So slice mode is dependent on device mode, but block mode will be dependent on slice mode or perhaps something in device mode. So that's the sort of the simplified example, and to give a little bit of code here, which will not dwell on too much, but effectively we have a new device mode that has 3 possible modes, and a slice mode that has 6 possible modes, along with the associated random variables, device mode and slice mode that you're going to use to get what the value of each of these possibilities are. And then we have one constraint that's applied to the device mode that selects from one of the two or the 3 possible modes that device mode could be. And similarly, we have another constraint for slice mode, which, depending on which device mode you select, will ultimately select which slice mode you get. And as you can see, I've ignored quite a bit of stuff here, including if you wanted to specifically order that device mode is solved before slice mode. Obviously, ways you can ensure that this bidirectional constraint ensures that you create your device mode, and you select your device mode first. That's the concrete example, and here's some concrete code. So get that in your head. But basically, the essential ones are that we created a random variable and a random constraint for each of these elements that we want to randomize. So let's imagine that we're going to go through our process of layering devices. So what are layering constraints? So in the first one, we want to consider just layer 1, and we want to ignore all the variables and constraints that are in layer 2 and 3. So first thing we do is we turn on the rand mode and the constraint mode for the variables and all the other constraints and all the other variables that have been attached to layer 1. And then we disable all the variables by turning off the rand mode and constraint mode for all the variables and constraints that are found in layer 2 and 3. And then we, similar to the pre-randomized call, we'll call a layered pre-randomize, which is essentially the same thing. It's the idea or the same intent as the pre-randomized, which is where you want to do something before you start the randomization process. And then we finally call the randomize. Now, what the randomize does, because we turned on the constraints and the variables for layer 1 and turned off the constraints and variables for layer 2, it'll randomize this entire object, but it will only randomize the variables and constraints, or it will only randomize the variables using constraints from layer 1. And layer 2 and layer 3 will be completely ignored by the solver. So that's the completion of layer 1. So at that point, layer 1 now, all its variables are now set. they've been randomized and constraints have been applied, and they're all set. So now we're interested in what happens with layer 2. So in a similar way, except now we want to ignore the variables in layer 1 when we present the constraints to the solver. Because we want to tell the solver, okay, layer 1's already been selected, don't change that. So we do that by turning off its randomization and its constraints for layer 1. So these layer 1 variables are now what I term state variables. So they're like constants. And layer 2 now can use those variables as if they were constants. So now we're randomizing layer 2, so we want to turn on its random variables and its constraints. And then, as you can probably imagine, layer 3 is similar to layer 1, where we want to ignore it this time. So we turn off all of the variables and its constraints. And now we do the randomize. Now, at this point, layer 1 variables are now considered as constants. Layer 2 are the variables that we want to now randomize according to the constraints that are attached to layer 2, and we want to ignore layer 3 completely. So effectively, we're supplying to the constraint solver layer 2 with layer 1 as constraints. And so we get the randomization values for layer 2, and it's complete. And layer 3 is a fairly, going through this repetitively, you can imagine what happens is the same thing as previously. We disable the constraints by turning the rand mode off, the constraint mode off for both the layer 1 and 2 variables. And now these are all state variables that layer 3 can use in its randomization. And same as before, layer 3 is the one that's being randomized, so we turn on its rand mode and its constraint mode. We call it randomize. And when we present this whole object to the constraint solver, layer 1 and layer 2 are fixed, and layer 3 now is randomized according to whatever values are found in layer 2 and potentially in layer 1. And at that point, all the layers have been randomized. So you've got variables selected from layer 2, layer 1, layer 2, and layer 3, and the ordering has been defined by which layer you attached the variables and constraints to. And at the end of all that, you randomize the entire object. In a similar way you would call post-randomize, you call layer post-randomize for the same intent. You want to adjust values perhaps in the object that's been randomized, and you can do that at this point. That's essentially it. Now, what I want to show you is what it looks like in practice. And this is using macros to define both the layers and which layer each variable and constraint is being attached to. So we use the use models very similar to the UVM fields macro, where we have a begin and end statement, and then inside there we have another macro that basically has the layer that you want to attach the variable to and the variable name, or similarly the variable or the layer you want to attach the constraint to and the constraint name. And you do this for all your variables and constraints that are being controlled by this layered constraint methodology. All right, so let's break that macro out and to show you what it does. So the layered constraints begin. What it will do is it will create two main things. It will create the current layer, which is just basically an integer value, defining which layer you're currently in. So this becomes a new data member of whatever your config or whatever class you're randomizing. Similarly, we create a new virtual function called toggle layer constraints that takes one input, which is what is the current layer that you're randomizing, or the toggle layer that you're randomizing. And that's the end of the begin macro. So yeah, we'll create a new function member of your config class. And the next thing is the layered variable. This macro simply takes the device name, or sorry, the variable and the layer that you want to attach that variable to. And it expands it out into, takes the variable name, takes its rand mode, and then depending on the toggle layer that is passed in, it will either turn the rand mode on or turn the rand mode off. And in this case, because we said that layer and device mode is attached to layer 1, it will take that one and it'll check that, when we're in layer 1, we'll enable the random. When we're not in layer 1, we will disable it. Not surprisingly, I'll show you how that sort of pulls into the macro. And then the layered constraint macro is very similar, except now it's dealing with the constraint mode rather than random. Same idea, depending on which toggle we are currently trying to toggle or randomize in this case. If we are in layer 1, the device will see constraint mode be turned on, otherwise it will be turned off. And then the layered constraints, so that's how they all sort of fit together. And then the layered constraints end, all it does is it closes off the function declaration for the toggle layered constraints. So now we have a data member called mCurrentLayer and a new function called toggle layered constraints, which we'll use in the randomize layers. So this is the macro that you would call when you want to randomize the 3 layers in this case, and we're doing it against the config object. So you pass it in 2 variables, the handle to the object that you're trying to randomize, and the number of layers you want to randomize. In this case, there's only 3 layers, we will randomize them all, so we pass in 3. What that explodes into, perhaps not surprisingly, is an iteration. You want to go through the first layer until the last layer, and you want to call this toggle layered constraints function that we just created on the class that you're trying to randomize. So what this is doing is it's basically turning on and turning off the variables and constraints as I showed earlier. So for layer 1, it will turn on all the layered 1 constraints and variables, and layer 2 and 3 will be ignored. And we go to layer 2, same thing. And then finally, we randomize that object, ensuring it succeeds. So remember that this variable was added to your configuration class or your object that's being randomized. And this toggle layered constraints expands out into, as I indicated, when we're in toggle layer 1, we turn on the rand mode, and we turn on the constraint mode. That's the part. And that's it. That's it for the randomize. Now there's more debug code that we've added into the randomized layers to do stuff, and there's a couple other steps that are ignored, but that effectively is the end of it. And so the paper goes into more details about the use model that we've had, especially goes into more details of what the macros entail. And there's more, as I indicated, there's more debug information in those macros. And there's also another sort of nuance macro where you need to control the layered constraints from a test case. It's very, very similar to above, but there's just a slight difference in terms of how it's done. As I said, the paper goes into greater details about how that works. And as I indicated, there's debug information to allow you to, as you're going through each layered randomization, you'll get an idea of what was randomized, what constraints were turned on and turned off, and gives you a little bit more detail about when you have a constraint failure of any kind. So that's essentially the gist of the layer constraints. As you can see, it's fairly straightforward. It's a simple application of controlling the random mode and constraint mode for each of the variables and constraints you want to apply to each of the layers you want to do. Future work. So I wanted to go into a few slides on what we plan to do to extend this functionality a little bit better. One is we had a common maintenance issue, as you can probably imagine, by using numbered layers. So if you wanted to add a new layer, say between 2 and 3, you want to add a new layer between these 2 and 3 layers. Then what would happen is you'd have to update all the layers from 3 onwards to increment their numbers. So all the layers that were previously 3 now are 4, 4 becomes 5, and so on and so on. And you can add your new layer 3 in. That turned out to be a little bit of not a nightmare, but it was just annoying. So going forward, what we were thinking of doing is basically attaching a named layer rather than a numbered layer. So in this case, we would have a common layer, which would be the first layer, the mode, which would be the second layer, and per slice, which would be the third layer. And the idea behind that is you would have one associative array that indicated the ordering of each of these named layers. So it would the randomization order would depend on the value of the associative array that's pulling in the name. So now all layers now are not attached to a number, they're attached to a name. So as you can probably tell, when you add a new layer in, between 2 and 3 in this example, the named layers don't change, just the one spot needs to change, and that's this associative array that indicates now per slice and all the other slices after per slice are now incremented by 1. But you only do that in one spot rather than multiple files across your entire environment. And then you add your new layer in, naming it whatever you want, and then just indicating that it's now layer 3, or it's third in the ordering of the randomization. There's also, as I said, we didn't have time to refactor our constraints in object-oriented, to allow any object-oriented methodologies like policy classes to be used, to allow us to selectively pick which constraints we want to apply. But I think we're going to be exploring and have been exploring a little bit of how these two methodologies could cooperate, if you will. So basically having object-oriented techniques of selecting which constraints you are going to use, and then using this layered constraint methodology to basically to indicate how the ordering of the constraints are done within each of those dynamic set of constraints. Maybe we'll have a feature paper on that. We'll see. The other future work is just, the debug can always be improved. So what we want to be able to do is two things. One is add, right now the debug goes out into your log file, into a very large file, and you have to sort of sort through what it's doing. I think what we'd like to do is every time we create a new layer, is create a new file. So it makes diffing between layers 1 and 2 very easy using just sort of standard diff tools. The other thing that we'd like to do is create a kind of tree. As I indicated in all my diagrams, there's a pyramid, basically. Layer 1 variables, are the smallest piece of the puzzle, and then layer 2 builds on layer 1, so there's more of those, and layer 3, and so on and so on. So I think by adding a simple piece into the macro, we can create a diagram showing how the constraints can all depend on each other and how the per layer values are associated. And that's it. So thanks very much. I talked a little bit about why, why you would need to have the ability to layer your constraints or selectively pick which variables are randomized. There are, pointed out, a couple of object-oriented approaches of policy mixin. I think those are the first and best approaches to use. This solution that I've presented is, we think it's kind of pragmatic in terms of taking an existing set of constraints and variables and applying them to a particular layer, and then being able to control how each layer is sequentially randomized. And future work, as I indicated, we want to sort of improve on the maintenance side of things by using named layers and improve debug. And that's it. Thank you very much for your time, and appreciate your interest in the paper. Thank you. Bye-bye.